friends, in the last session we had a look at the different shapes that molecules can have, and we said, just very basically, just to recap, we said that the covalent compounds can be divided up into specific shapes depending on how many bonding pairs of electrons and how many lone pairs there are on the center atom. We then said that single pair repulsion is the strongest, bonding pair is the weakest. All right. And we found then that molecules can be pushed into specific shapes. Carbon dioxide forms a straight line. We say that molecule is linear. All right. Most of the covalent compounds that consist of two atoms will be linear. Then we said water. Can anyone remember the angle that there was between the hydrogen, oxygen, hydrogen on the water? I think it was 107 or 104.5. Okay, we'll have a look at them in a moment. But we said then the water molecule is V-shaped. Ammonia, NH3, is pyramidal, and methane is tetrahedral. Now we are going to have a look at them as we do in theory. Okay. Now, what is important is that carbon forms the center atom. We have two bonding pairs there, two bonding pairs there, two single pairs, two single pairs. We will find that the repulsion on both sides of the center atom is the same. All right, and it will push the angle between the oxygen, carbon, oxygen into a straight line there. All right. So the repulsion of the oxygen atoms is the same. Therefore, the bond angle is 180 degrees, forming a linear shape. Very important, the name of the shape. Then from that, we can go and have a look at the water. We see here that the oxygen has got two single pairs which repel each other strongly in 3 dimensions, as far away as possible. Then we have a bonding pair over here, bonding pair. So the repulsion between bonding pairs and single pairs is also fairly strong, but not as strong as between the single pairs only. So that also pushes the hydrogen atoms away downwards to one side. The repulsion between this bonding pair and that bonding pair is very weak, so they can't repel each other very strongly. And as a result of that, we find that the bond angle over here is going to be 104.5 degrees. Now you need to remember the size of the angle. Okay, they won't ask you obscure examples, but you need to know carbon dioxide, water, ammonia, and methane. All right, it's just basic classical, or the classic examples for V-shaped, pyramidal, tetrahedral. Okay, so water then is 104.5 degrees, the bond angle. The next molecule that we have to have a look at is the ammonia molecule. Remember, it's NH3. So in the ammonia molecule, we have got 3 bonding pairs that repel each other fairly weakly. All right? So the repulsion over here and over there is not very strong. And, well, over there, remember, it's 3-dimensional. It's not very strong. We only have 1 single pair over here. So we don't have single pair repulsion like we had in water. All right? We've only got single pair, bonding pair repulsion, and bonding pair. That is why we find that the bond angle in the ammonia molecule over there, that angle, is slightly bigger than in water, because the forces pushing those hydrogens down to one side are slightly weaker. So the angle over here is 107 degrees. Same over there as well, 107 degrees. All right. Okay. The last one, we call the shape then of the ammonia molecule, where we have a single atom over here and 3 on the bottom forming a triangular base. We call that triangular pyramidal or just pyramidal. All right. There we go. Is a pyramidal shape. Then methane is probably the easiest one to explain of the lot. Are there any single pairs of electrons? No. We have 4 sets of bonding pairs. There's one set, there's another set, and another set. And we find now that the repulsion between these pairs are fairly weak, but it is the same in 3 dimensions. There's not a force pushing it stronger from one side of that molecule. So these carbon-hydrogen, the hydrogen-carbon-hydrogen angles will all be the same size, and they will be as far away as possible that they can get in 3 dimensions, forming an angle of 109.5. So, try and remember it. Water, 104.5. What was ammonia? 107. And the last one that we've done now, 109.5. So 4, 5, 6, 7, 8, 9. Okay. Try and get yourself a system to remember the size of the bond angle. If you can remember the sizes, you would be able to figure out which size belongs to which atom. Why is the bond angle in water smaller than in methane or ammonia? Because in water, we have got single pair repulsion that pushes the hydrogen atoms down. You follow? All right. Why is the angle in ammonia bigger than the angle in methane? Methane only has bonding pairs which repel each other equally weak in all directions, while in the ammonia molecule there is one single pair that repels the bonding pairs fairly strongly away. All right. So you need to try and remember the size of the bond angle. Okay, people, now we've had a look at ionic bonding. We've had a look at covalent bonding. Now we're going to compare the properties of ionic compounds and covalent compounds. Now the physical properties of these compounds have got to do with the strength of the forces between the particles. What makes it sometimes difficult to understand, if we have an ionic compound, we have a crystal lattice that consists of positive and negative particles, and you can all understand that opposite charges attract. So we said then that in an ionic compound, the forces over here between the particles, what are the particles? Ions. What forces do we have between ions? Are Coulomb forces. Okay, the Coulomb forces are fairly strong. All right. Now, when we're going to have a look at molecules, it's slightly different. A water molecule, for argument's sake, will have that shape. So here is the whole water molecule. Within the molecule over there, we have a covalent bond. It's a chemical bond. But if I have 2 water molecules, what forces exist there? Those are weak. Van der Waals forces. All right. Between molecules, we have weak forces. Between ions, we have the ionic bond. It's a chemical bond. It's strong. All right. No matter how big my salt crystal is, whether I have one as big as a grain of sand or I have one as big as a block that I go and put out for the kudus to lick near the water, okay? The salt crystal is held together by ionic forces, electrostatic forces between ions. It's a strong chemical bond. But with molecules, we differentiate. We talk about intermolecular between two molecules. The inter-Cape bus travels between Cape Town and Windhoek, the inter-Cape. But within the molecule over there, those forces there, let's do them in a different color. Those forces, that is an intramolecular force. It's a force inside the molecule, and that happens to be a covalent bond, which is strong. Covalent bonds are strong like any other chemical bond is strong. But I think what confuses you eventually is the fact that when we work with ions, it's easy to understand. The forces between the particles are just Coulomb forces, forces between charged particles. But when we start working with molecules, we have to differentiate two types of forces. The chemical bond within the molecule. And that one does not determine melting and boiling point. Okay? The forces between the molecules are the ones that determine melting and boiling. You need to understand this concept very clearly. My fingers are bonded onto my hand. Okay? I can't break off a finger very easy. That's like the forces inside the molecule. But my two hands can be held together by weak van der Waals forces. All right, it's an image. Okay, so it's not within the molecule. It's between the molecules. All right, and from that we can differentiate specific physical properties. People, ionic compounds, we've done this in previous years. What are the properties of ionic compounds? They are all solids and they are all hard and brittle. So if you hit them with a hammer, they will shatter. All right. Why are they hard and brittle? We have strong forces between the particles. If there are strong forces between the particles and I want to try and make that solid melt, I'm going to need lots of energy to give the particles enough energy to vibrate far away from each other to overcome the forces. So we find then that ionic compounds have high melting and boiling points. People, they are really high, 900 degrees, 950, 2015 degrees. Okay? They have very high melting and boiling points. The reason being strong electrostatic or Coulomb forces between the particles. Ionic compounds, they can conduct electricity, but not in the solid state. Because why? In the solid state, the charged particles are held fixed in a crystal lattice. All right? To be able to conduct electricity, the charges must be able to move. So when I melt a salt, or when I dissolve a salt in water or any other liquid that it dissolves in, we will find then it will conduct. All right? The reason why water conducts electricity, the water coming out of the tap, is there are salts dissolved in the water. So it's actually not the water that conducts, it is the dissolved salts that are the charges that can move. And the moment you have moving charge, you've got electricity, current. No? Pure water won't conduct, it's molecular. All right, so it will conduct in the melted or dissolved state, and it's important to state that. Okay, because later on when we do the metallic bond, metals will conduct whether they are melted or whether they are solid. Okay, so you must distinguish. They will conduct when the salt is melted or dissolved. It does not conduct when it's in the solid state, because the charged particles are held in a crystal lattice. Okay. Covalent compounds. Remember, the forces between the particles are weak. So, if they are solids, they will be soft. Mothballs, for example, are molecular solids. What happens to mothballs if I leave them on the shelf, open outside of the packet? Doesn't dissolve? What's the process called? Doesn't evaporate? Yes, it undergoes sublimation. It goes from the solid state directly to the gaseous state. Why doesn't it go to the liquid state? The forces holding those particles together are so weak that the moment the particles get enough energy, they can go and become a gas. All right. So, if they are solids, they are soft solids. Usually we will find that any of the covalent compounds that we work with are liquids, or, there's a typing error, or gases. People, if we look at things like HCl, HCl is actually a gas. We work with it as hydrochloric acid, but that's the gas dissolved in water. That is why when I open up the bottle of HCl, it immediately starts giving off fumes. Ammonia is another one. NH3 is actually a gas at room temperature. It dissolves in water. So I can add it to Handy Andy to help clean up fatty deposits, etc. But when you work with Handy Andy, you immediately smell the ammonia because it wants to become a gas again. Things like hydrogen sulfide is a gas. Carbon dioxide, CO2. The only one I think that you really work with that is a liquid, or not even work with, but that you know of, is bromine, diatomic molecule. It's a liquid. Iodine is a solid. But iodine, just like mothballs, if I have a crystal of iodine and I start heating it, it doesn't melt. It immediately becomes the gas. All right, so the forces between those particles are very weak. That is why most of them are in the form of a gas. The ones that are liquid would be my organic compounds, because the molecule gets a little bit bigger and a little bit heavier. Okay, and then they require a little bit more energy to make them evaporate. So things like ethanol is a liquid, methanol is a liquid. Okay, carboxylic acid is a liquid. Okay, those ones then, but we won't work with them at this point. When we do organic chemistry, we will work with those ones. All right, so they, because of the weak forces, they will have low melting and boiling points. You understand that? Requires very little energy to be added so that the particles can overcome the attractive forces. They use the term low volatility. In other words, they will evaporate very easily. Okay. Low boiling point goes together with low volatility. It simply means it will evaporate very easily. For example, if I have diesel in a puddle and I've got petrol in a puddle, the diesel is going to take longer to evaporate than the petrol. Okay, petrol is more volatile than the diesel. They do not conduct electricity. Okay, why don't they conduct electricity? What is electricity? Current. Moving? Charge. Are there any charges that can move? No. All right. So there are no charged particles, so it cannot conduct electricity. And the last one, mostly not soluble in water, while the ionic compounds are mostly soluble in water. Now this last one, there are quite a few exceptions to the rule. In general, in chemistry, we say, like dissolves like. Something will dissolve another substance if the forces between the particles are more or less the same size. Does that make sense? Because if the forces between, let's say I've got a liquid, and the forces between the liquid particles are very strong, and I'm trying to make a solid substance dissolve in it, if the forces between the solid substance is not strong as well, they can't move in between each other. All right, so like dissolves like, there are a couple of exceptions. Normally, for example, if I take sugar and salt, if I take petrol Petrol is a molecular substance. It's a hydrocarbon. Sugar is also a hydrocarbon. Sugar can dissolve in petrol. If I took normal table salt is ionic. Table salt does not dissolve in petrol. Why? The forces between the salt particles are much stronger than the forces between the petrol particles. Do you understand that? Now, water messes us around. Water is actually a very, very special compound, and you've done that last year already, where we said we look at the melting point of ice and what happens to, why does ice float on water? Because it expands between 4 and 0 degrees. Okay, now water, because of its very special shape that it has, and because of the 2 single pairs of electrons that don't form a bond, we find that the water molecules, the forces between them, the water molecule is almost, it isn't an ion, but it's almost an ion. Okay, it's got a slightly negative side and a slightly positive side. We'll have a look at that later on as well. So we find that water can sometimes dissolve molecular substances, and other times it can dissolve ionic substances. For example, if I add water to petrol, will they dissolve? No. But if I add sugar to water, will it dissolve? Yes. You understand? Okay, so there are many exceptions, but just as a general rule, like dissolves like. Right. Okay, so those then are the properties of ionic compounds and covalent, just very general properties. Now, the next term that we have to have a look at is something called an allotrope. Nice new definition. Have you done allotropes before? Nope, you've not. So allotropes, they are different crystalline structures for the same element. And a very, very well-known example is diamond and graphite. They are both made out of carbon. But we get 2 different crystalline forms. They are formed under different conditions. Diamonds are formed under very high pressure and very high temperatures. All right? Usually in the columns of volcanoes with a molten rock and organic matter that is burning, all right, and sublimating. When it cools down and there's no oxygen present, then we can get the formation of diamonds. Graphite is formed under different conditions. Graphite is the stuff they put in your pencil lead. If you have a lock that sticks, you buy graphite powder and you puff a little bit of graphite powder into the lock. It acts as a lubricant. Okay? Both are made out of carbon. Now, we will go into the specific shapes of diamond and graphite in one of the next units. All right? So, there's a third allotrope for carbon, one that is called Buckminster Fullerene, or just very simply shortened down to buckyballs. Okay. The Buckminster Fullerene consists of 60 carbons covalently bonded onto each other in structures that look like a soccer ball. You follow? The patches on a soccer ball? Okay, 8-sided. Buckminster Fullerene look like a soccer ball. So it's a hollow ball of carbon. All right. We will go and look at materials that are made with them and things in one of the next topics. I don't want to start with that now. Just a little bit more about Buckminster Fullerene, or just Bucky. They will accept both. It shouldn't be a problem. They sometimes refer to them as fullerenes as well. They are homonuclear. What does that mean? Homonuclear. The same nucleus. What is heteronuclear? Different nuclei. In other words, bromine is homonuclear, diatomic, same bromine and bromine. But HCl is heteronuclear, a hydrogen and a chlorine. Okay, so Buckminster Fullerene are homonuclear because they consist of carbon atoms, identical carbon atoms. They can be spherical, okay? That's their natural form, the buckyballs. And we can open them up and we can build them into structures like tubes, which we will go and have a look when we do different materials. And this is where we get the carbon fiber materials, etc., that are very strong, and so on. The spherical fullerene contains 60 carbons and are called Buckminster fullerene, or buckyballs, while the tube fullerenes are known as nanotubes. Where have you heard about nanotubes? They're investigating nanotubes in terms of conductivity, because graphite conducts, and the nanotubes are made from the fullerene, that they tend to, make them build onto each other to form long tubes. And these tubes can conduct electricity. There is less resistance in a nanotube than there is in a copper wire. All right, so in terms of, yes, at this point it is expensive. All right, but it's where the new research is going into. Okay, fullerenes are used as drug delivery systems to the body, lubricants, and catalysts. Now we'll have a look at that when we get there at this point. There's a check your progress, page 135, that you have to do for me for homework. All right?
Akili, 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 akili. We love to wash our hands, and this is how we do it. Wash, wash with clean water. Scrub, scrub, scrub with soap. Rinse, rinse with clean water, and then the germs will go. We love to wash our hands, and this is how we do it. Wash, wash with clean water. Scrub, scrub, scrub with soap. Rinse, rinse with clean water, and then the germs will go. Yay! Well done, soap and water! You got rid of all the germs on Achilles' hands!
Grade 10s. Yesterday we stopped where we had a look at the crystalline structure of sodium chloride. Can you remember I said to you, each sodium ion is surrounded by 6 chloride ions in 3 dimensions. And each of those chloride ions are surrounded by 6 sodium ions, and it forms a cubic structure. All right. It's very difficult to see it on the diagram, but if we look at that one, it is surrounded by 1, 2, 3, 4. Which one? That one? Yes, okay, there. We go 1, 2, 3, 4, 5, 6. All right. So each ion is surrounded by 6 ions of the opposite charge, forming a very dense cubic structure, and that makes the crystalline structure of sodium chloride quite unique. All right. Now, the properties of ionic compounds. Now remember, usually a lot of the properties of these compounds go back to the strength of the forces between particles. The moment we have charged particles, like we do have in ionic compounds, we find that the forces between charged particles, opposite charged particles, we call them electrostatic, or what type of forces? Yes, Coulomb forces. Okay, electrostatic or Coulomb forces are usually strong. All right, Coulomb forces are fairly strong, relatively strong. Therefore, we find that ionic compounds, because it's ions attracting each other by Coulomb forces or electrostatic attractive forces, they are hard, brittle solids. They have high melting and boiling points. All right, and they will not conduct electricity in the solid state, but they will conduct if they are melted or dissolved. Who can explain that? What is electricity? Okay, current is moving charge. Okay, so in the solid state, why can a salt not conduct? The charged particles are held fixed in a crystal lattice by strong forces. But when they are melted or dissolved, these forces have partially been overcome and the particles can slide off each other or over each other. And we find then that melted or dissolved salts are able to conduct electricity. Examples of ionic substances: lithium fluoride, sodium bromide, potassium chloride, etc. Now I want to do the bonding of these ionic compounds. Now, can you remember how we show ionic bonding? The first rule always is write the formula, all right? How do we know how to write the formula? Let's say we want to do lithium fluoride, okay? We need the elements lithium and fluorine, and then we have to go and check the number of bonding places. Lithium lies in group 1, so it has 1 bonding place. Fluorine lies in group 7, so it has 1 bonding place. So we will need 1 each. All right, so we need the formula. The second step, write the Bohr structure of the elements. So lithium is element number what? Lithium is element number 3. So it has 3 electrons. 2 in the first shell and 1 in the outside shell. Fluorine, we're not yet there yet, has how many electrons? Fluorine's got 9 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9 electrons. Okay, now in the third step, to show the ionic bonding, we only work with the outer shell electrons. And fluorine, let me do it in a different color so we can see. 1, 2, 3, 4, 5, 6, 7. Okay, now, what will the metal do? It is going to lose its electrons. Where will that electron go? To the non-metal. So we show fluorine loses an electron. Lithium loses an electron. It goes to fluorine. And we show the electron in the fluorine shell. Okay. You don't show it in the lithium shell. So lithium becomes +1 and fluorine becomes -1. All right. And we have electrostatic forces of attraction between those elements. We can write the equation of what happens. We said lithium has 1 outer shell electron and it forms a lithium ion plus 1 electron. And now I've got them in the wrong color, okay. Fluorine has 1, 2, 3, 4, 5, 6, 7 electrons. It's going to gain 1 electron and it is going to form fluorine. 1, 2, 3, 4, 5, 6, 7. There's the one that's gained -1. And what do we end up with? Lithium ion plus a fluoride ion gives me lithium fluoride. Okay? Yes, this is actually how you get to this. All right, next one. What other examples did I have over here? Sodium bromide. Let's do another one. Potassium chloride, sodium. Let's do aluminium sulfide. Okay, aluminium and sulfur. How many bonding places does aluminium have? Aluminium has got 3 bonding places. How many bonding places does sulfur have? 2. So now what do? We cross over. So the formula would be, come on, go, 2 aluminiums and 3 sulfurs. You with me? Okay, so the next step, draw the Bohr structures. So we have aluminium is element number 13. So aluminium will have how many electrons? 13 electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9. 8 in the second, so it's 10 altogether. 11, 12, 13. How will sulfur look like? Sulfur has got how many electrons? 16. So 1 shell, 2 shells, 3 shells. 1, 2, 1, 2, 3, 4, 5, 6, 7, 8. So that gives me 10, 11, 12, 13, 14, 15, 16. With me? And now we show the outer shells. We show that aluminium has got how many electrons in its outer shell? 1, 2, 3. All right? Okay. So sulfur has got how many electrons in its outer shell? 6. 1, 2, 3, 4, 5, 6. So what is aluminium going to do? It's going to take its electrons from the outer shell. And how many aluminiums do I need? 2 aluminiums. So I need to draw in another aluminium over here with its 1, 2, 3 electrons. And how many sulfurs do I need? The formula tells me I need 3 sulfurs. So sulfur and sulfur with 1, 2, 3, 4, 5, 6. 1, 3, 4, 5, 6. Okay, so that one will go there and there. And now I need to get there. It's going to go. One will go there, 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 and there, and there. What was me right in by aluminium? It has become +3, and sulfur has become -2, or 2 minus. All right. Yes, and then we can go and write the equation. We can go and say, oh yes, we have to draw the arrows. Yes, okay. Write the equation. If we say what happens to the aluminium. Aluminium had 3 electrons. What did it do? It lost them. All right. How many aluminiums did we have? Yeah, so we have 2, 2, and 6. Because it breaks up. We started with that and we ended with that. But where did those electrons go? We say sulfur has got how many electrons? 6 electrons. It's going to gain 2 electrons. Do you agree? And we have sulfur, 1, 2, 3, 4, 5, 6 electrons. And the 2 that it's gained. How many sulfurs are there? 3. So I need how many sulfurs here? I'm just showing you how it goes. We need to say 2 aluminiums plus 3 sulfurs give me, just look what I've shown you over here. I've simply said we started off with an aluminium. There's the aluminium that had 3 electrons. There are my 3 electrons. 1, 2, 3 outer shell electrons. But what did the aluminium do? It lost the 3 electrons. So there's the aluminium. No. Because this is reagents, that is products. So we started off with an aluminium with the electrons in its shell, and we ended up with an aluminium without electrons in its shell. They are separate. Okay? No, plus. That gives me that. Okay? I multiplied it with 2 because we have 2 aluminium. And if we have 2 there, we need 2 there, and it will give us 6 electrons. The sulfur had 6 electrons in its outer shell. 1, 2, 3, 4, 5, 6. And what did sulfur do? It took from each aluminium 2 electrons. So we show it took 2 electrons, and if it takes 2 electrons, it's going to become minus 2. All right? But how many sulfurs did we have? We had 3. So 3 sulfurs means there are 6 electrons, and we will get 3. And right in the end, what actually happened? We had an aluminium ion, 2 of them, and it attracted 3 sulfur ions to form aluminium sulfide. The final equation you can show. Let's do sodium oxide. All right, sodium oxide, first step, write down the elements. Sodium and oxygen. How many bonding places does sodium have? 1. How many bonding places does oxygen have? 2. So we need to have 2 sodiums and 1. Do we show the 1? Nope. Go away. All right. Now we need to draw the Bohr structures. Sodium. How many electrons for sodium? 11. 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, 1, 2, 3, 4, 5, 6, 7, 8. Them away. 1, 2, 3, 4, 5, 6, 7, 8. And there we have 11. And then the oxygen. How many electrons does oxygen have? 8. 1, 2, 3, 4, 5, 6, 7, and 8. Okay, now, how many sodiums must I draw? 2 sodiums. Okay. How many oxygens must I draw? 1 oxygen. How many electrons did oxygen have in its outer shell? 6. What did the sodium do? It gave its electron, and we end up, yes? All right, and then lastly, we write the ionic equation. 2 sodium ions react with 1 oxygen ion, forming Na2O. Any questions? Are you okay with that?
Black sunrise, always gonna be a surprise, 'cause we don't know the way it's going to go, 'cause we can see the way it's going to be, 'cause we can see.
We're talking about COVID. So, Regine, tell us about the day you found out you had COVID.
The day I found out I have COVID. It was a difficult day. I didn't understand how I got COVID, because I was always covered, I was always with my hand sanitizer. It came with my wife. And that whole day, I was thinking, what's gonna happen to me? I'm gonna survive. My kids. I was losing my tasting, smelling. There were some days I will test my taste buds. and put like 4 or 5 chilies in my coffee. No ways. I didn't taste it.
So did you also lose your appetite in the process?
It was very funny. In the first week, no, I was chowing. Like I will wake up like midnight and make for me something. But after the first week, then the appetite was gone. When you go to bed, your body is also automatically switching off. And that's a dangerous time for COVID. It's like glass pinching you, cutting you inside your lungs. Then the heart was pumping like rubber pumps. You are losing a lot of fluids at night.
Is that through fever or what?
Yeah, it's through fever.
So have you experienced any side effects from having contracted COVID-19?
No, not yet. Maybe still coming, but not yet.
And your wife?
She was complaining about light head. It's an annoying headache. It's light, but it's annoying.
So basically you didn't take any prescribed medicine from the doctor to recover from COVID?
No, I didn't. The only thing I was using is desperate for my blood not to clot. Because for some people, when your lungs are really, really infected, your blood will start to clot from the lungs, close all the airways. That's where we are passing. I'm smoking cigarette, and when you were a smoker, and COVID in your lungs now.
So then after you found out, you both found out you had COVID, what did you guys do to protect the kids?
The kids move out from the house. The Buddhists will come, then we will collect everything for them and just put for them outside. When they came, just grab the food and go.
So what was the biggest battle for you? Was it mental or physical?
Mentally. Mentally was the biggest battle. I'm actually an international movie maker, and my career was cut off. I couldn't put bread on the table. There were some days have one meal for the day, then went to bed. And that was hitting me in my mind. What if Blessing get corona now? Where am I gonna go? Who can I help? There were also some people depend on us in the rural areas. We couldn't help them. My future was black, dark, dark, dark. I couldn't even see that small light at the end of the tunnel. One day, my daughter decided, now, I want to see my father today. And I just told her, yeah, she can come. The first words was, Daddy, I was praying for you yesterday night. Don't worry, Corona will go back soon. And I was asking, from where? From Namibia? She said, no, not from Namibia, from you. And you are not looking good. And she was actually heartbroken. Until today, she hates Corona. From there, then I was like, oh, okay. If the smallest one is saying this, why am I not picking me up self and do the right thing and get rid of this thing? That's where I started to run, to practice, coming to my quiet place. And actually, the main thing that broke my heart during that time was there was no one. The time of COVID, there was no one.
So can you tell us where we are right now?
We are at my silent place. I call this place my silent place. I will come here when the COVID is hitting me like 120%. Looking at the ocean, then you will hear voices like, no, you don't belong here. Today you don't belong here. Get up and go home. Some days they will nurse you like, no, you will survive. Your future is a bright future. You must not give up now. Think about your kids. Think about the people around you. Even the wind will do that. Actually, you must meditate The thing of COVID is, looks like COVID is afraid of the warmness and is friends with the coldness. So the whole time you are baking in the sun, it helps a lot.
So is that what you did?
Yeah, I did. I will do that twice a day. This was supposed to be a golden year for me. A very, very good golden year for me. But then COVID decided, no, this is not going to be your golden year. Everything was cancelled. We, the film makers, this year, from the international shoots, lost lot of money.
You've lost 3 family members? Is it all due to COVID?
No, not all due to COVID. First one, my sister. She was very close to me. She contracted COVID April, and she was in ICU for 3 months. The COVID damaged her lungs, and at the stage her lungs collapsed and she couldn't breathe without the machines. Her kidneys failed, her liver has failed. COVID is real. First of all, COVID is real. It's not a joke. Most of the people, they fall away from COVID regulations. Still early to fall away from COVID regulations. We must still go in line with those COVID regulations.
And how long did you say it took you to recover?
3 weeks, 21 days.
What must somebody do to change your mind from that negative perspective to that positive?
COVID, no job, it's very dangerous. There was one day I just decided I'm gonna take a rope, go to the jetty, sit around there, and after all I will hang there by the jetty. The time I arrived here, there was no wind. Out of nowhere, the ocean was like angry, and it started to get cold, and I was like, but it was just nice weather. Then I sat down. Then the universe will talk with you, the wind, the sun, the ocean. That's the main thing of COVID. If you don't save yourself, no one will save you. And we must always appreciate what we have around us. That's the main thing in COVID. If you don't appreciate what you have around you, no, you will lose your head.
Smile, smile, smile. When you walk with me, I just want you to smile, smile.
My industry and what I've done with my hands in Namibia, it's going all over the world, and here you are, Papa G, you want to quit? Now, I'm excited for 2021. It's not gonna be the same like 2020 now. I'm making back in the groove.
Give me food, clothes, water, and shelter. Nothing else, no matter. You're my moonlight in my oven. Let all my sins be forgiven. Happiness rain on me. Never let the children cry.
The coronavirus that causes COVID-19 has changed since the pandemic started. So does this mean the virus has become more dangerous? Scientists have discovered thousands of mutations to the SARS-CoV-2 coronavirus. Most mutations only lead to small changes, but scientists believe one, called D614G, may have made it easier for the virus to infect human cells. This mutation most likely emerged after the initial outbreak in China, and it spread fast after the virus arrived in Europe. By the end of June, the D614G mutation was found in almost all samples of the virus worldwide. Scientists believe this is due to amino acid changes in the virus's spike proteins, improving its ability to infect human cells. Some studies have found more spikes on viruses with this mutation. These spikes latch onto receptors on the surface of our cells. They then transfer the virus's genetic material, called RNA, inside. Being inside the host cell allows the virus to make many copies of itself. Random errors sometimes happen in the copying process, which cause mutations. Although the full effects of D614G are still unclear, some studies suggest that the mutated virus might be more transmissible than the original. This could mean more people getting sick and at a faster rate. Despite this, there isn't any evidence that the disease itself has become more severe. Scientists are worried about mutations possibly increasing the risk of reinfection. Hong Kong reported what could be the first case of virus reinfection on the 24th of August. A healthy man in his 30s is thought to have caught the virus again 4.5 months after he first got sick. During this time, mutations developed and new variants of the virus emerged. Some experts believe these changes may have made reinfections more likely. Mutations are common over the course of a pandemic. New flu vaccines are needed every winter to keep up with genetic changes to the flu virus. If a coronavirus vaccine is found, it could require regular booster jabs. Mutations won't happen overnight, and the coronavirus is mutating slower than the flu virus. But it's important for scientists to keep a close eye on how the virus changes over time. Could we be hearing more about other mutations in the future?
My name is Ban Ki-moon. I am Secretary General of the United Nations. I was born in Korea. I was 6 years old when the Korean War started. We had to run from our homes to the mountainside. We could see my village burning. The United Nations saved my family and my country. In my time as a Secretary General, I have been moved by the horrors of humanity, and I have been inspired by his heroes. I have wept at the memorials for victims in Auschwitz, Srebrenica, and Rwanda. I have dealt with tragedies that have gone on for decades, and disasters that destroyed whole societies overnight. I've also mourned too many courageous United Nations staff members who died serving the cause of peace. I believe in having a young mindset. This means standing up to injustice. I hope I will never be too old to ask leaders tough questions. I hope I will always have the energy to speak out for what is right. I think that keeps us young.